first. Yeah, let's do it. Let me first introduce you. Yeah. Welcome everyone to today's ASP seminar. Today we are happy to invite Zuri Liu, a professor from the University of Minnesota, Twin Cities, to talk about a recent paper, Give Me FP32 or Give Me Depth, that's on the impact of numerical precision to a reasoning evaluation. The is mainly work on the large language model and their applications, focusing on enable them to combine and process information from diverse sources and domains. For that reason, he deeply care about efficiency, reasoning, long context ability, and understanding their inner working mechanism. He is also very interested in extending foundation models to other domains, exploring the interplay between and different sources of data. Let's welcome Zuri for today's talk.
Okay, thank you for the invitation. Yeah, I want to say I watched lots of the past events in the ASAP seminar. I think this is a great opportunity for people to discuss like sequential modeling and also the architecture go beyond transformer. But today I will mainly talk about, today my presentation is focused on numerical precision and discuss how this niche affect the performance and also the evaluation of recently very hard reasoning model. So this is a joint work between me, my group at the University of Minnesota, and also the researchers and collaborators from Rice University and Adobe. And I'll also attach the QR code for the code base. Okay, so in this talk, I will mainly explore three research questions. The first one is numerical stability. As you know, is a very long-standing problem in our computing area. But why reasoning model is much more sensitive to the numerical precision compared to other machine learning models. And also, I will discuss what factors impact the final results and introduce actual variance and uncontrollable factors that impact your final reproducibility. And also, what are the potential solutions to this problem? And so this talk is a little bit, so because this is a largely a empirical report, so I want to show the suggestions I made in this paper to the entire audience, just in case if you are not interested in the technical details. But I hope this can be adopted by the researchers in the communities for a better reproducibility. The first thing is that, okay, so if we want to use greedy decoding for ensuring a token level reproducibility, by token level reproducibility, I mean you can have a token by token reproducible reasoning trees. So if you want to have this, please run it in 32-bit precision. And also, I want to emphasize one more thing is that unlike final accuracy, so I know recently the long to short research is pretty hot. So if you want to, for example, for other people to reproduce the token length you have in your paper, so you should, if you use greedy decoding, you should better use floating point 32-bit precision, because this token length is very sensitive to numerical precision. And second one is that for more commonly adopted random sampling based evaluation, like top P nucleus and or top K sampling method, I suggest run it with more trials, especially for smaller data set like AIME or AMC. And my suggestion is we should do it at least 16 trials per answer for this small data set. And later I will show why I give this specific number. And also, I think in the community, we should report standard deviation and error bars for a better understanding how significant it is for the results. Okay, so let's begin the main body of the talk. So I will mainly first introduce the background regarding numerical precision and also our key finding and suggestions on the reasoning evaluation. And finally, I will discuss some insight why reasoning model is so sensitive compared to other non-reasoning model. Okay, so I will first introduce what is IEEE 754 data format. IEEE, so besides IEEE 754, actually we have lots of different numerical format, but IEEE 754 is one of the most commonly used data format for representing real numbers. So in this numerical format, we mainly have three parts: the sign bit, the exponential bit that represents the numerical range, and the number of mantissa bit controlled per session. So usually speaking, the more exponential bit you have, then you can represent a number with larger range. And for the format with a large number of mantissa bit, you can express the percentage. You can express the number more accurate with better precision. So almost all recently released model, we commonly use the BF16 numerical format, or it's often called BF16. So because the model was trained using this precision, so during the inference, people commonly adopt this BF16 numerical precision. So you can see because the IEEE 754 is only with limited precision. So that means at each operation, you have something called rounding error. Uh, uh, and in the community, so we commonly adopt a low precision inference. So this is the data sheet I copy pasted from NVIDIA website. This is for the H100 GPU. So you can see, roughly speaking, if you have tensor core, you have better throughput in terms of T-flops. If you lower the numerical precision, it will also give you higher throughput. So here, for example, if you lower the numerical precision, say from FP16 to FP8, you roughly double your throughput. So because you reduce the I/O volume and also the computation burden. So that being said, in the community, because of the NVIDIA hardware, the low precision inference is the commonly adopted practice. But low precision have one problem is that IEEE 754 have limited precision. So that means at each operation, you have something called rounding error. And because rounding error, actually your arithmetic is not associative. So for example, if you change the order of sequential summation or sequential multiply, the result is not identical actually. So here I show one interesting rounding error example. So for example, this is I use PyTorch 2.6.0 and I think I know, or it's more like I believe this error still this bug still stands in the PyTorch and also NumPy. So if you input one number like 8.125 and if you use floating point 16 precision and you have another number is 1032. If you ask PyTorch A plus 100 1024 whether it equals B or not, actually it will return you the answer is true because it's rounding off the fraction part. If you're curious why this happens, I write one blog about the rounding error. So this is not like this is not because PyTorch problem. This is a fundamental problem with IEEE 754. And you can see this problem is very severe and definitely we already got lots of the efforts on dealing with this problem. So for example, on the algorithm side, we have some very powerful sequential summation algorithm called Kahan summation. And also there is one very famous numerical robust accumulator called exact dot product accumulator. This is from the algorithm side, and from hardware side, actually, NVIDIA GPU, they already have the hardware primitives to deal with the rounding error. So for example, one of the very famous CUDA FMA. FMA is short for fuse, manipulate, and add. This is also one screenshot I taken from the website. You can see in the FMA, we have only one rounding step instead of two rounding steps. So that means they will reduce the rounding errors if we using this FMA. But unfortunately for the reasoning model, although with this algorithm and hardware solutions, we still got some variance when we changing the system configuration. So this figure is one illustration example when we use DeepSeek Q1 model, which is a Q1 7B model distilled from the reasoning trees generated by DeepSeek. So you can see in this case, if we change the evaluation batch size or GPU, the number of GPU we used for tensor parallel, or the hardware version, like we changing from A100 to H100, these factors will change the model results under greedy decoding. Uh, the greedy decoding means we pick the next token deterministically. So ideally, greedy decoding should be deterministic. But you can see due to if we change the system and hardware configuration, we change the floating point arithmetic order and changing the rounding error, and finally it will change the token ranking and cause the results to be undeterministic. And this is one illustration example. So for example, if you change the batch size, the model can give you completely different answer. So that being said, I don't suggest using gradient decoding, especially for reasoning model. Okay, so this is the background on the numerical procession. And I will move to our key finding and suggestion on the reasoning model evaluation. So here I will first introduce some commonly used decoding strategy. The first one is greedy decoding or maximization-based decoding. This method uh, is deterministic because we choose the token deterministically with the highest probability. And the second one is top P or nucleus sampling. So in this method, we set a threshold P and only sample from the top token with with cumulative probability less than P. So usually speaking, for this number, we commonly so nucleus sampling is one of the mostly commonly adopted decoding strategy. So the P is often set as 0.9 or 0.8, so 0.8, something like that, to eliminating the long tail tokens. And also the top K sampling. So top K sampling means we set a threshold K and only sample from the top K tokens. So for example, if we set K equals 20, that means we only sample from the top with the 20 tokens with the highest probability. In this way, we're eliminating the long tail tokens. So these three strategies are arguably most commonly adopted evaluation or decoding strategy. So with this decoding strategy, the community often adopted two evaluation settings. The first one is that for greedy decoding, we report the single run accuracy because it is deterministic. Because the greedy decoding is deterministic, so we only need to run it only once, right? And report the final run accuracy. For random sampling based method, we usually run it with multiple trial and report the averaged accuracy or the pass at K evaluation metric. So our experimental setting is that because we know we want to study the numerical procession impact to the model, because we know floating point arithmetic is not associative. So we want to change the hardware and system configuration to trigger the change of the order of arithmetic. So for example, if we change the number of GPU or the tensor parallel size, a GPU version, or evaluation batch size, changing them will impact like the macro level token scheduler, underlying kernel selection and implementation. and then we essentially changing the floating point arithmetic orders. And we control the software to be the VLLM 0.8.2. Okay. Uh, One more thing regarding this kernel selection is that usually speaking for example, if we're using PyTorch actually they will route to different kernel according to your matrix size. So and also even for one single operation like matmul, we have different implementation like split key or non-split key, but this is too detailed. I will skip the details here, but basically you can think it in this way. So uh, commonly adopted machine learning system, they will dynamically select the kernel according to your problem size. But if you change your TP size, you will split your model weight in different way, such that they will be routed to different kernels. And different kernel, they definitely got different numerical stability. This is some background. Um, Here is our key finding or key suggestion. So first, for the graded decoding, we actually show that if we change the hardware and system configuration, they can actually significantly change your final accuracy. So for the uh, non for example for the math 500 or live code bench, this data set with hundreds of questions, the accuracy standard deviation is often at 2%, something like that. But for smaller data set like AIME or AMC, the accuracy standard deviation can be up to 10%. So that being said, graded decoding is not deterministic and it may have significant change according to your data set. And for the random sampling based method, we show that hardware and system configuration can often introduce extra 0.3 to 2% standard deviation. And I think this is especially harmful when researcher doesn't report the error bar. And later I will illustrate why I say this. So first, for the I show some uh, concrete number here, because for the ease of illustration, I only take a screenshot of two data set. Actually, if I remember correctly, we do more experiment in the main body of the paper. So you can see from the number here, if the data set is small, the BF16 standard deviation can be 9%. That is super large because AIME, this data set is very small with only 30 questions. But a very interesting thing is that for non-reasoning model, you can see the accuracy change, although still with 30 questions, it's around 2% accuracy standard deviation. But for larger data set, like mass 500, you can see the accuracy change is 1% to 1.5. But usually speaking, it's around 2%. And again, for non-reasoning model, the accuracy change is much smaller. And if you're changing your numerical precision from BF16 to floating point 32, then you can see the accuracy change is almost zero. So that being said, if you want to, for other people to have a token level reproducibility, so that being said, then you can have the token by token exactly the same reasoning trees. I suggest using higher precision like floating point 32. So instead of just using BF16. And second, for the random sampling, and actually in this paper, we mainly evaluate the top P sampling or nucleus sampling. So you can see the accuracy. So N here refer to the number of trials we generate per questions. So you can see the BF16 for math 500 is 0.3%. And I want to mention that this accuracy is purely from the hardware and the system change. It's not like the inherent randomness from the sampling process. This is how we do that. We actually, in each system configuration, we run it with 4 trials, and we calculate the average accuracy. And across different system and hardware configuration, we calculate the standard deviation of the average accuracy. So ideally, if your sampling process is super stable, the standard deviation should be 0, because ideally, no matter what is the system, no matter what is your hardware, you should get the same average accuracy, right? So this number actually refer to the variance caused by the hardware and system configuration. I want to make that thing clear. So you can see, in general, uh, the hardware and system configuration can introduce actual 0.3 to 2% standard deviation. And here you can see, if you run your experiment with more random trials, the standard deviation can be significantly uh, reduced. So here, for example, for the AIME, this dataset, if we run each question, which we generate 16 answer per questions, the accuracy change, sorry, the standard deviation is around 2%. If you improve your number of questions you generate per question to 64, then the hardware impact will reduce to like 0.4%. So this is some concrete number regarding the reasoning model and the non-reasoning model. And you can see, ideally for the FP32, the accuracy, the standard deviation can be almost 0. That would be the thing we want to see. But I also mentioned that in the random sampling case, the most effective way to reduce the hardware impact is running more trials. Though it is much more effective compared to increasing the numerical precision. So that's the reason why I mentioned we should we should report both the accuracy and error bars in the paper instead of just the average accuracy. So I say this because in the if you are familiar with statistical machine learning, actually we have something called 95% confidence interval, right? So if we assume your noise is Gaussian distribution, so that being said, they are white noise. So if you want to have a 95% confidence that your results is better, actually you require 2 sigma accuracy improve. So if you can imagine that if your standard deviation from the hardware is 2%, you need at least 4% accuracy improvement to demonstrate your method is significantly better than the other, right? So this is at least 2 sigma. So if you want to 100% or 19, if I remember correctly, 99.7% confidence interval, you need a 3 sigma. So you need 6% accuracy improvement. So that being said, in my opinion, we should report both the accuracy and also the standard deviation in order to better understand whether our improvement is significant or it may just caused by some hardware or system lottery tickets. So we don't know if we do not report the error bar. Okay, so in summary, our finding is that for greedy decoding, people usually report a single run accuracy, but changing the hardware and the system configuration can, like GPU, the number of GPU or a GPU version, can significantly change your final accuracy, especially for the reasoning model. And the system and the hardware configuration is actually out of the control for the users. So because some user they have like A100, some user they just have 3090. You cannot control that. So it's very difficult for other people to reproduce your results if uh, using the if we're using greedy decoding. But evaluation bias is indeed something we can control. If you want other people to reproduce your results in the graded decoding, you should run it in FP32. That's our one suggestion. Second, for random sampling based method, people often report the average accuracy and also the pass at one. But actually, the hardware and the system configuration, again, they can introduce actual variance. And in my opinion, it is very harmful when researchers do not report the standard deviation or the error bar because it's very hard for other people to distinguish whether the improvement is significant or come from the hardware lottery. Okay, that's the suggestion I personally mentioned. So I will stop here a little bit just in case you have any questions regarding the experiment setting or the numerical possession before we move to the analysis part. For example, why reasoning model is such insensitive. Okay, I will move to the last section. So in all our experiment, we consistently find that the reasoning model is actually more sensitive to the numerical errors compared to the non-reasoning model. It makes sense because the reasoning model they generate more token, right? So for example, the reasoning model often generate 32,000 tokens. So that being said, small numerical error can accumulate in your KV cache and get snowballed to trigger the final token ranking flips, and then your final results is not deterministic, right? But here I want to share more insight. Uh, in what case uh, the model is very sensitive. Okay, so I will starting from one motivating one. Suppose your token distribution is one hot. So that being said, if you assign 100 probability to one single token, all other tokens have zero, almost zero probability. You can imagine that in this case, no matter you are using sampling or greedy decoding, it is very sensitive, it is very robust to your numerical error, right? Because rounding error, still they are rounding error because then their magnitude is super small. So small magnitude error cannot trigger, for example, one hot distribution to be to distort such a one hot distribution, right? So even with the small rounding error, you cannot change the ranking of top one and the top two token. And also in the sampling, still you sample this token almost with 100 probability. No, nothing changed, even with the small rounding error. So the bad case is that if your token probability is very close to each other, you can imagine, for example, for greedy decoding, you can imagine small rounding error may trigger the flip of your token ranking, right? Because in greedy decoding, the only thing matter is the relative order of the token probability. So if with some small rounding error, if your original top one and top two token probability is very close to each other, and the small rounding error is could be large enough to trigger the flip of your token ranking. Right. So actually, we found that for at least for graded decoding, this is indeed the case. So the model also have a very high entropy probability distribution and small rounding error. And actually for if you're using BFC the rounding error is not that small actually. So the rounding error cost to the logic is sorry, not the logic. The final probability can be up to 5% change. So you can imagine in some extreme case, some probability go down 5% just because the rounding error, and some probability go up just because of rounding error, and then the exchange the order, and finally your results is not deterministic. And very similarly for you can for top P and the top K token, because they also rely on token ranking, right? So for example, top K token means we only sample from the topmost K token. So if some small error trigger the token ranking change, then that means we will sample from different candidate pool. So that will definitely introduce actual variance. So and similarly for the top K sampling. So they may occasionally exclude or include more long tail tokens. So because greedy decoding is much easier to analyze, I can show you the one concrete example. So the answer one and the answer two is generated from the same model, same system prompt. The only change is the hardware and the system configuration. And you can see in the answer one, the top one and the top two token uh, is very the gap between them is around 5%, something like that. But if you just change the system and hardware configuration due to some randomness in your computation, they can be almost exactly the same probability, unfortunately, in practice. And that's the reason why you have non-deterministic greedy decoding with this reasoning model. And this is also the case for the top K or top P sampling. You may the candidate pool can be significantly different just because the rounding errors because they all rely on the token ranking, and token ranking is sensitive to small rounding error, especially when your distribution is uniform. And my feeling is that to me, this is not a bug. This is not a bug. This is more like a feature of a reasoning model. Because during reinforcement learning or supervised fine-tuning, we have many high entropy minority tokens. And actually, I have observed that. So especially, this is exactly the case that the model have. So this is especially the case that um, both token can be make sense in the current sentence. So for example, when they are reasoning, either they can continue their uh, in their like repetition or the continue the current reasoning trees, or they stop it, move to the next one. So and in my opinion, I think both of them they make sense. So actually, in reasoning model, they have many such high entropy minority tokens, and it is very and in if this is a and in that position, they are very sensitive to the rounding errors. And in my opinion, I think this makes sense because uh, this is how reinforcement learning work, right? Because in reinforcement learning, we first need to sample lots of the different behavior, and then we increase the probability of the behavior lead to better accuracy and penalize the probability of bad action lead to worse accuracy, right? So that being said, during the reinforcement learning, we need diversity. We need the answer diversity to ensure that we sample a good number of uh, high quality reasoning trees. And in order to have that better diversity, we need higher entropy token distribution. So that's my feeling that this is not a bug. This is more like a feature of reasoning model. So in summary, I mentioned I will talk about three questions in the talk. So the first one, the numerical stability is a long-standing problem, but why reasoning model is very sensitive? In my opinion, two reasons. First, high entropy of some minority token. Second, they generate too much tokens and the error can get accumulated. So traditional discriminative model or the non-reason model, they also have this problem, but they are not severe enough to trigger a notable accuracy change. And second, what factors impact the final results? In my opinion, anything change your floating point arithmetic order that will trigger the actual variance, like GPU version, GPU count, your evaluation batch size. So what are the potential solutions? So first, for the greedy decoding, if you want to have a token level reproducibility, please use floating point 32. So that will give you much better token by token reasoning trees reproducibility. And second, for random sampling based method, please run it with more trials and report the standard deviation. Um, okay, that's all the thing I want to cover in the talk. I'm happy to answer any questions.
We have a question in the chat.
Let me check. Any inspection on which layer? Oh, I see. Uh, Great questions. Actually, I can share some of my insight. So actually, I have at least tried all linear layer using floating point search. Actually, I do this ablation study. So for example, I try to do all linear layer in 32 bit per session and leave the like uh uh layer norm and also the embedding layer and also the rope in lower precision. This doesn't help and 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 vice versa. So in my opinion, probably the final head layer is very sensitive. So the final head layer should definitely using floating point 32, in my opinion. And for all other layer, I didn't do a very like apple to apple check for the uh, numerical error or the extra variance. But at least I know if you just change all linear layer to floating point 32, still you still got non-deterministic gradient decoding.
Yeah, I think like just a recent paper called Minimax M1, and they show that like the LM height layer should be in FP32, and that is very beneficial for precision.
Yeah, I think so.
So I had a question about sort of, isn't the precision problem really very much like a variance problem where, as long as you control for the variance, then like the effects of precision don't matter as much?
Very good question. I also think about this problem. So for example, I can elaborate one case when it is not a precision, when it is not a variance problem. So, for example, for the random sampling, we commonly adopt nucleon sampling, right? So in nucleon sampling, we exclude the long tail tokens. So if your numerical precision is, so for example, if you are using, let's say, LP4, say for example, suppose LP4 is super random, and then it will just by case occasionally exclude or include more long tail token or include or exclude a different set of candidate tokens. So if this is the case, it is uh, it harm the variance but also your accuracy because if with different set of candidate tokens, definitely your final accuracy is not the same. But I can see that. But I can see a few words regarding this is that at least for BF16, I didn't know. I didn't. So different candidate set doesn't have much for your final accuracy. This is a variance problem for now for the BF16. But I'm not sure whether this is also again the case for LP8 or LP4. This is not something we need to run it in order to know the final results.
Yeah, no, I mean, I was asking because of the Munich paper.
Hmm.
Yeah.
Yeah, great questions.
Actually, I had another sort of thing from the Munich paper, which
Yeah.
is like, because they show that not accuracy, that variance scales by 1 over k relative to position k.
Mm.
And so, you have later tokens have higher variance. And so I was wondering if that would be, I mean, I guess it's different than what you observe in terms of the reasoning models being more sensitive, but I think that could be an additional factor.
I see. I see. Sorry. You mean which paper?
Munit, let's see, this, what's it called exactly? Um, unit scaling, simple and scalable FP8 LLM training is the paper.
Oh, I see. I see. Can you send
Yeah, I'll put it in the chat.
yeah, I want to mention the training and inference is very different in my opinion because training, uh, in my opinion, is much more robust to like numerical position error because
Hmm.
so for example in the training we for example we can adopt the dropout and also like stochastic rounding techniques because in my opinion neural network training process we are using uh, SGD, right? So SGD itself is random, is a random based method. So actual error in the numerical position, in my opinion, doesn't harm that much. Uh, but you can see still people use the automated mixed precision, right? We use FP32 to accumulate, or we use FP32 to store the model weight in order to mitigate the rounding error from the low precision. But in general, I think training is much more, in my opinion, much more training process itself is much more robust to rounding error because it is random based. But for sample, but for the inference, because people want, so we want the reproducibility, right? We want to, for example, at least for me, I want to, for example, have the identical number uh, can be reproduced on my own computer compared to the paper reported in the paper. So uh, that's the reason why I think like token level reproducibility and also the variance um, is very important.
Um, I have a very practical question. So do you think like
No, go ahead.
pre-training is more robust to precision than the decoding stage?
Oh, this is a very good question. I have the feeling that pre-feeding is more robust compared to decoding. Why I have this feeling is that Uh, if for some task, it is essentially just run the perfecting. So for example, selecting the A, B, C, D, this kind of task, you essentially just run one single pass perfecting and then you get the final answer. So my feeling that for that kind of task, it is very so it's pretty robust. But for decoding, in my opinion, is because we have KV cache. So um, you have the running error in your past K and V, and every run there the the error is different. And with more token, then your KV cache getting larger, and also the running error, and at some point it just snowballed. This is my feeling.
I see. But I think like for flash attention, it does not support FP32.
Yeah,
So
that
if we have to use FP32 during this pre-training, and it may and when the prompt length is like kind of long, and there may be some memory issue, right? Because we
yeah
have like existing kernels to avoid the materialization of that
yeah
attention matrix.
yeah, and I also think, in my opinion, LP32 prefitting is probably never come because I know that for for perfecting it requires some like hardware feature from NVIDIA GPU, like LD matrix, something like that. But this operation doesn't support FP32. So actually, if I want to run FP32 inference, I need to change the backend to X former in the VLLM. But in general, I think this is a great question, whether we can, for example, changing the profiling precision to LP16, and also when we need to a more detailed ablation study which part is sensitive to numerical errors.
Yeah, that would be amazing. Yeah, I think like currently the most simplest way is just to change your LM head weight to FP32.
Yeah. And in my opinion, if we use random sampling or nuclear sampling, actually we can just use BF16, but just run it with more trials. This is the most effective way. Let me check. Okay, the question is accuracy to perplexity. Very good questions. I don't know. I didn't run this experiment. Yeah, I think definitely different metric, they got different sensitivity. So continuous metric, yeah, continuous metric is more robust, makes sense to me, because it's not like discrete 0 and 1. And if you just change the token, then you get the wrong answer. Yeah, that makes sense.
Are there any questions? Yeah, I think that we don't have further questions. And thank you again for your presentation. I think like this precision issue everyone should keep in mind this precision issue during the evaluation of reasoning model. Yeah, to make the true progress of in this field. Yeah, thank you again.
Thank you. Okay, see you.
See ya.